We will have to deal with three types of three-dimensional integrals in this course. Those are line integrals, surface integrals and volume integrals. The example of a line integral is the work done by a force on a particle. As a particle moves along its trajectory, the net work will be the sum of all elements of work dw done along every infinitesimal small displacement dr. As you should know from first-year physics, the work is given by the dot product of the force and displacement. The line integral is just the sum of those infinitesimal elements of work over the trajectory line. All the elements are scalars, so the integral is also a scalar. Next, consider a vector field on a surface. We can define an infinitesimal element of surface ds as a vector whose length equals the area of that element and whose direction is normal to the surface. Next, we can define the infinitesimal element of flux as the dot product of that vector field E and the element of surface ds. The total flux of the field E over the surface S will be given by the sum of all those infinitesimal elements of flux dp. That is the surface integral. The surface integral is also a scalar, but it can be either positive or negative, depending on whether the vector field goes into the surface or out of the surface. That, of course, will depend on how we assign the positive direction to the surface when we selected which way the elements of the surface point. That is arbitrary. But there should be no sudden jumps. Two nearby elements of surface should point in the same direction. Finally, consider a scalar field in a volume. For example, that field can represent a local mass density ρ distributed over the volume V. Then we can define the infinitesimal element of volume dV given by the cube with sides dx, dy and dz. That volume will be just the product of those lengths. The infinitesimal element of mass then will be given by the product of that element of volume dV and the local mass density ρ. So that the total mass will be given by the sum of all infinitesimal elements of mass contained inside this volume. That is the volume integral. It could also be used to find the total charge contained inside some volume from a known charge density distribution. There are two important theorems which we would often use in this course. They relate various three-dimensional integrals and differential operators. One is the divergence theorem. Consider some field E existing in a volume V. The lines of field penetrate the surface enclosing the volume S. Divergence theorem states that the volume integral of the divergence of the field equals the total net outward flux of the vector through the surface that bounds the volume. It relates the volume integral to the surface integral and will be used quite often in this course. The second theorem is the Stokes theorem. It relates the surface integral of the curl of a vector field with the line integral of the field itself. Consider a field E existing on an open volume V. Stokes theorem states that the surface integral of the curl of V over the open but bounded surface S is equal to the closed line integral of V along the contour bounding the surface. Both the divergence theorem and Stokes theorem simplify the mathematics when it is necessary to evaluate volume, surface and line integrals. They will also be used for connecting differential and integral forms of the Maxwell equations.